Good afternoon. So let's do a little bit of review what we have covered so far, okay? In terms of entropy, the second law of thermodynamics. Okay, we started the second law of thermodynamics and entropy. Okay? So basically, as I mentioned in the previous lesson, before entropy, before second law of thermodynamics, everything was based on conservation principles. Conservation of mass, conservation of energy, first law of thermodynamics, zero law of thermodynamics, right? But in the second law of thermodynamics, I've said that it is not a conservation of principle. It's not a law. It is a statement of properties. And we introduced Clausius and Kelvin Planck statements, right? They were basically talking about if you need to achieve a cycle, right, you need two thermal reservoirs at a different temperature, right? One from receiving, one from to dump the energy or the temperature or the heat in that manner, okay? And then what Clausius was saying that in a cycle, in a cyclic cycle, right, in a cyclic process, dq, right, over T is less or equals to zero at max, right? And by knowing that, we demonstrate to show what Clausius means by dq over dt over a cyclic process equals or less than a zero by introducing a thermal reservoir connected with a series of processes. One was a reversible and other one was a piston cylinder assembly, if you remember the demonstration. Okay. Okay. To demonstrate the validity of a Clausius statement, dq over dt is less than a zero or equals to zero at max, we worked on this, right? And we wrote our energy equation and we ended up a new property, entropy, correct? And how did I know that this quality was a property? Right? I also show that if I have a piston cylinder assembly, correct? With volume and heat, centimeter heat, you can pick any integer in front of it, right? And I said, if I extend this to any volume bigger than the previous one, right? And come back to my previous one, basically, initial state, right? My volume change overall is zero, right? This means that it's a path-independent process, right? And I know as a fact that volume is a property, correct? So this has to be a property. In the perfect cycle, which was the reversible case, correct? This has to be a property. I don't know what that is, but it has to be a property, right? And then Clausius said, let's call this an entropy. Okay? And this from state 1 to state 2, or any state, this quality over T, or dq over dt equals 0, right? Best mass is the entropy change between the states. Okay? Okay. Any questions so far? Okay. So we also started a problem. We introduced some okay, let's start from the beginning. The Clausius inequality dq over t is less or equal to 0 if we apply this to a cycle, okay, where less than 0, sorry, where less than 0 stands for irreversibility process, and equal sign equals to 0 stands for reversible ones, right? And we also talked about Carnot efficiency. The Carnot efficiency, he introduces a Carnot power cycle. Carnot power cycle, where I have the maximum efficiency of that cycle possible I can reach, right? So if we take a heat engine, piston cylinder assembly, okay, one to two, two to three, process 1 to 2, process 2 to 3, process 3 to 4, and process 4 to 1. Okay? This piston cylinder assembly is insulated, right? And is connected to an insulated stand, insulating stand. Second one is hot thermal reservoir. These are all insulated. insulating stem, whole thermal reservoir. So from state 1 to state 2, I apply adiabatic compression at a constant volume. State 1 to state 2 is an adiabatic compression. 1 to 2 is adiabatic compression at a constant volume. Okay. State 2 to 3 is isothermal expansion at a constant pressure. State isothermal expansion 3 to 4 is adiabatic expansion. 4 to 1 is isothermal compression. At a constant pressure. Okay. Okay. What happens in the first process, okay, it's an insulated, I only increase my pressure. Remember, this is a Carnot power cycle and it's the most efficient one. It's the most efficient one. Okay. From state 1 to state 2, adiabatic compression at a constant volume. State 2 to 3, isothermal expansion at a constant pressure. State 3 to 4 is an adiabatic expansion at a constant volume. Okay. Process 4, state 4 to 1 is an isothermal compression at a constant volume. Okay. So if you introduce irreversibilities into the cycle, right, you will get a deviated process. So your shape will be deviated rectangle or square. It wouldn't be square, but it will be deviated. Okay. So from here, from state 1 to state 2 for adiabatic compression, right? So d Q over T equals 0. There is no heat interaction in the system. From 2 to 3, isothermal expansion, right? With T takes heat from a hard thermal reservoir. Okay. And we talked about all this. From 3 to 1, 3 to 4, adiabatic compression, right? dQ over T equals 0. And from 4 to 1, the process is isothermal compression, dQ over T equals QC over TC. Can you see? Okay, from here, we also introduced all these in the previous lesson. Okay? So we will again introduce in a different way, and we will go back to our problem we ended our class in the previous lesson and imply all this. Okay? Any questions? No? Okay. Clausius inequality in the system is reversible. So the integration, cyclic cycle, cyclic process, the Q over T equals H over QH over TH plus QC over TC equals QH over TH minus QC over TC equals 0. For a reversible process, this integration of dq over t equals 0. Then it adds current into D, right? For an reversible power cycle, dq over th will be equal to qc over qh. Clausius inequality, irreversible. Let's consider an irreversible heat engine operating between the same hot thermal reservoir and cold thermal reservoir as the previous reversible engine. Remember, Carnot had two corollaries. Right? First one was if you have two power cycles, one of them is irreversible and other one is reversible, he said as long as they operate between the same thermal reservoirs, irreversible efficiency of an irreversible power cycle will be less than the reversible power cycle. Right? We mentioned that we showed it between two thermal reservoirs. Right? And second corollary was, if you have same ambience, both are reversible, functioning between the same thermal reservoir, efficiency is the same. Remember those? Okay. So Clausius inequality and irreversible, so we are basically stating the same thing, showing from a different way. Okay. Same power cycles, we're just going to look at from an irreversible point of view. We're going to introduce irreversibility on those power cycles. Okay? So, integral of dq over t, okay? When the system is irreversible, remember, this value is negative. Right? So qh over th plus qc over tc equals qh over th minus the absolute value of the qc over qc is less than 0. Tc over th is less than QC over QH. Power cycle efficiency. Let's recall what power efficiency was. Right? We call it with a eta. Thermal efficiency was 1 minus QC over QH. For a reversible cycle, for reversible Carnot cycle, right, the efficiency 1 minus Tc over Th. This is also called Harmonic efficiency, right? Or I also know that Tc over Th equals to C over Th. So you can replace it for reversible Carnot cycle. And for irreversible Carnot cycles, efficiency of the cycle should be less than 1 minus C over Th. And I also know that Tc over Th is less than Tc over Th. We have introduced all this. Irreversibility. Instead of using a smaller symbol, right, let's use an equal symbol, but let's introduce irreversibility in the system and call that irreversibility something. Okay, so we can use all this equal. So to create an equation from the Clausius inequality, okay, we may write this dq over t term, okay, equals minus sigma cycle. Okay? Now instead of using 0, I introduce an irreversibility term which called sigma. Okay? That term has to be minus because dq is always less than 0 or 0 at max. Right? If this is 0, it's reversible. If it is an integer, it's irreversible. Right? So the sigma, the parameter sigma may be considered as a measure strength of the irreversibility. Or just the irreversibility. Okay. Any questions so far? So basically, we are just reviewing in a different way. Okay. Okay. But we also said that this term, by just looking at this term, I can determine what kind of system I have. Do I have a reversible system or irreversible system, right? If I have that term, the integer, I have an irreversibility. With most of the case. If this is 0, I have reversibility. And let's recall those again. Characteristics of irreversibility. Meaning that if sigma cycle equals 0, okay, there is no irreversibilities present within the system. If sigma cycle is positive, irreversibilities are present within the system. If sigma cycle is less than 0, it's impossible. The way I have introduced this in the previous lecture was through entropy. Right? This is through irreversibilities. They are reverse of each other. Okay? If you have irreversibilities, suppose that irreversibilities cannot be negative. Right? Entropy might. Entropy cannot be positive. Right? Let's remember that as well. So cycle, remember, okay, cycle through different reversible processes. Okay. The way I have introduced this new property, entropy, was going from state 1 to state 2, okay, following different paths. Okay. Let's call this one A, B, C. I have one way to go from state 1 to state 2. two paths to come back. From state 1 to state 2, Q over T, right, by using path Q, plus, in order for me to complete my cycle, I have to come back to my initial position, correct? Plus, from state 2 to state 1, Q over T through path C equals 0. Let's introduce the sigma, irreversible piece. Let's call this equal to 0. Now, let's go from state 1 to state 2 to path A, and come back to path C. So these terms are equal, right? Path C. And if I compare this to integrations, comparing the two equations, and say from state 1 to state 2, through which path A will be equal to, from state 1 to state 2, if I follow path B, Q over T. So this is another way of showing that dq over t is a property. Okay? It's a path independent. Right? So since both path A and path B are arbitrary except for being internally reversible, the integral of dq over t has the same value for any internally reversible path from point 1 to point 2. Therefore, it is a property. And it is called entropy. With the symbol S. And the entropy is defined in terms of change, S2 minus S1, dq from state 1 to state 2, dq over dt, the internal reversible process. The unit of entropy is kilojoules per Kelvin. In specific form, S2 minus S1 is equal to state 1 to state 2 integration from state 1 to state 2 dq over t. Internal reversible. The unit will be kilojoules per kilogram Kelvin. We can also use entropy to determine the characteristics of our system, okay, by using entropy change, as we did for the sigma change, okay, characteristics of entropy. Heat added to system, delta S is positive. Heat added to system dq over T. Q is positive, integration of Q. T is always positive, right? Temperature is always positive. And not even be zero. So delta S is positive. The heat rejected from system, delta is less than zero. For adiabatic reversible process, delta is equal to 0. Adiabatic irreversible process, delta S is positive. There are many conceptual questions about entropy, entropy change, irreversibilities can be asked. What happens if the heat added to the system at a adiabatic irreversible process? Will it expand? You can play all those processes, right? Isothermal, reversible, etc. I can show you an example. And now we can go back and look at our problem. So we have a power cycle. We have a power cycle operating between two reservoirs, receives energy QH by heat transfer from a hot reservoir at a temperature 2000 Kelvin, and rejects energy QC by heat transfer to the cold reservoir at TC 400 Kelvin. Right? We have two reservoirs. I know the temperatures at both reservoirs, and for each of the following cases, we are asked to determine whether the cycle operates reversible, irreversible, or it is impossible. Okay. We looked at the first case, right? Where QH is 1000 kilojoules, right? Heat transfer from a hot thermal reservoir is 1000 kilojoules. In work cycle, 850 kilojoules. Right? how do I decide if my cycle is reversible, irreversible, or it's impossible to operate? Remember, we look at the current efficiency. Right? In the first case, right, the system was impossible because the thermal efficiency was higher than the current efficiency. All right? Thermal efficiency was higher than current efficiency, so it's impossible. Case B, case B, okay. From first law, QH equals QC plus work net. I know that for a cycle. 300 equals 120 plus 180. Right? So it's a reversible power cycle. So that's the wrong problem. Sorry. Case B. Thermal efficiency, Qn minus Q out over Qn. Right, that's how I calculate my thermal efficiency per power cycle. Right, Qn, I know is 2,000 kilojoules minus Q out 400 kilojoules and Qn is 4,000 kilojoules, 2,000 kilojoules. And thermal efficiency is 0.8. And I've also calculated my current efficiency for the case A. They have the same current efficiency. I don't need to calculate again. Right? Current efficiency was 0.8, which makes this case reversible. Case C. Thermal efficiency equals work net over work net plus Q out. Right? But it's Q in equals work net plus Q out. I know work net and Q out, 1600 kilojoules over 1600 kilojoules plus Q out, 500 kilojoules for case C, which would give you 0.76. So it's irreversible. Case B, Actually, we don't need to do any calculation for KST, right? It's already given the efficiency, so it's irreversible, right? Let's get one more example. Any questions? Data listed below are claimed for a power cycle operating between reservoirs at 727 Celsius and 127 Celsius. Find out the temperature for my hot reservoir and cold reservoir. For each case, determine if any principles of thermodynamics would be violated. It's A, the heat transfer from hot thermal reservoir, 300 kilojoules, work cycle, 160 kilojoules, and the heat to a cold thermal reservoir is 140 kilojoules. Case B, QH equals 300 kilojoules, work cycle 180 kilojoules, and QC is 120 kilojoules. Case C, QH equals Q8 is 300 kilojoules, work cycle is 170 kilojoules, and QC is 140 kilojoules. I have a system which is connected with two thermal reservoirs at different temperature. Right? I have a power cycle, I have a work net, I have QH from a hot thermal reservoir and the cold to the cold thermal reservoir. And the temperature at the cold thermal reservoir is 127 Celsius, and temperature at hot reservoir is 727 degrees Celsius. I can right away calculate my current efficiency for this pod. Now I know my temperature is at the cold thermal reservoir, and I know my temperature hot thermal reservoir. The current efficiency is 1 minus Tc over Th. 1 minus Tc will be 400 Kelvin, and Th will be 1000 Kelvin. So Carnot efficiency for this power cycle will be 60%. Case A. For the case A, we are asked to determine if any principles of thermodynamics will be violated. Right? Let's start from the first law. Let's check our first law. The first law is satisfied. Q H equals QC plus work done, right? From a first law equation for power cycle. Is QH 300 kilojoules equal summation of QC plus work done? 160 kilojoules plus 140 kilojoules. This is right. So first law is satisfied. You can tell first law is satisfied. But it doesn't mean that my second law is satisfied. I need to check my second law and make sure I don't violate it. Okay? Let's see. Second law. Thermal efficiency of the cycle. Right, work net over Qn. Work net is 160. 160 kilojoules. Work in is 300 kilojoules. Means 0.53. Right? Thermal efficiency is less than Carnot. So it's irreversible. I satisfy my second law as well. I'm not looking at reversible or irreversible here. Right? How do I violate my second law? If it is impossible, I violate my second law. I satisfy my second law in either way, if it is reversible or irreversible. Okay? So case B. So first law, QH equals QC plus work net. $300 kilojoules equals this is 120 kilojoules plus 180 kilojoules. First law is satisfied. Second law, thermal efficiency. Work net over Qn. Work net is 180 kilojoules over Qn is 300 kilojoules is 0.6. I also satisfy my second law for the case B, and it's reversible. For the case A, it was irreversible, but I satisfied that. Case C. equation. Q8, let's QC plus work net, right? Q8 is what? 300 kilojoules. 140 plus 170. First law is violated. Okay. If first law is violated, you can't proceed anymore. Okay. You need to stay and satisfy your first law. First law is a basic. If you don't have a first law, you don't have second law. No need to check second law. Any questions? Is it more clear now compared to last week? Okay, it will get more clear and clear. But make sure you read the chapter and try to understand. Okay? So entropy balance for a closed system. For an internally irreversible process. Okay. Entropy change from state 1 to state 2 is Q over T, right? Integration of dq over T plus some entropy production, right? Sigma. So this guy over here, this is entropy change. Entropy change. This integration of dq over T, entropy transfer, from either hot thermal reservoir or to cold temperature reservoir. That's the entropy transfer. And this guy here, sigma, is entropy production. Entropy balance for an open system. Again, for an internally irreversible process. Okay. Now I need to write a general form as we did for first law and conservation of energy equation. Right? I'm going to do the same thing. Right? Enters, leaves, accumulation, right? Goes to the summation. Okay? But it will be in terms of entropy. So for entropy balance for open system, integration of d over t, right, is a rate form, plus entropy entering introduced into my system with inlet minus summation of entropy introduced my system through exit or leaving my system plus entropy generation or entropy production in my control volume should be equal to entropy accumulation in the system. This first term, the entire thing, this is entropy transfers this is entropy generation, right? Sigma control volume. These are all in grade form, right? Because we switched the open system. Now we have a flow equals the entropy accumulation. Entropy accumulation. Time variant term, right? If I have a steady state, remember this term is zero. If I don't have a steady state, you need to calculate this as well. Just like we did for open system. Same thing. Any questions? So just like we had for a work calculation, when we started thermal calculation problems, we introduced our PV diagrams, right? The way we calculate work was the integration of PVV, right? Now we're going to introduce new equations because of entropy. These are called TdS equations. Let's recall first law. First law was a stored energy in the system, change in the stored energy in the system is equal to Q minus work, right? In this plot. Or in differential form, this is du equals Q minus work. Right? I know my expression to calculate my work, right? dW, right, d work, is pressure times volume change in the volume, right? PdV. And from a Clausius inequality, remember that delta S equals dq over t, right? So now, for expression for heat transfer, right? dq equals T times entropy change. Let's now insert this dq and dw back to our first law equation. Right? dq equals dq minus dv. Let's insert this expression for work and heat into first law and solve for TDS. I'm trying to derive an equation in form of TDS. Okay? So TDS will be equal to du plus PdV. What I did was putting this dw and dq back into my first law equation. So TDS equals du plus PdV. And I can also write this by using my enthalpy instead of my internal energy. Let's recall the definition of enthalpy, right? H equals U plus PV. Right? Take differential over dH equals du plus PdV plus VdP, right? And combine this with my TDS, first TDS equation. And TDS equation will be dH minus VdP. Okay. Now I have two TDS equations. Is this clear? Does everyone understand what I did here? Okay, I wrote my first law equation, right? d equals dq minus dw, right? And I introduced my dw, which was, what was my dw? PdV, right? I inserted PdV instead of dw, right? And I also know how to find my heat transfer dq from a second law of thermodynamics, right? That delta S equals dq over T, right? dq equals delta S and T, right? TDS, sorry. Right? I also inserted that in my first law expression, right? And I left my TDS alone, and I found my first TDS expression. And that first one was in terms of internal energy, and I said I can also find my TDS expression in terms of enthalpy, and I introduced my enthalpy and inserted that into internal energy, and I found my second TDS expression, which is dH minus dT. Okay? Any questions? Yes.
So the differential between the pH
Right. Okay. If you don't have any questions, this is all for today.